Safety is not added to an instrumentation and control design after the drawings are complete. It is built while choices are still flexible, hazards can still be removed, and redesign is still affordable. When safety decisions are delayed, risk does not disappear. It becomes a construction problem, an operating problem, a maintenance problem, or eventually an incident investigation. Your first safeguard is not a shutdown system. Your first safeguard is a sound basis of design. The basis of design must establish governing requirements, site conditions, operating modes, automation philosophy, shutdown and isolation strategy, availability targets, secure power needs, abnormal operating requirements, future expansion, and the boundary between normal control and safeguarding. If these foundations are vague, every later document inherits uncertainty. The control and shutdown philosophies must then explain how operators interact with the plant, how alarms are prioritized, how abnormal situations are handled, and how the facility moves to a safe state. These documents are not administrative paperwork. They are the contract between process intent, control logic, operator action, and protective response. Functional logic must be visible, testable, and understandable by someone other than the original designer. Cause and effect relationships, trip actions, permissives, overrides, resets, and safe state behavior must be documented clearly enough for another engineer to configure, review, test, and maintain the system without guessing. Testing must also be designed, not improvised. Supplier testing, factory acceptance testing, site acceptance testing, pre-commissioning, commissioning, and integrated functional testing must prove the complete protection chain. Sensors, logic, alarms, power supplies, communications, final elements, diagnostics, and operator displays must be tested together. Records must clearly show what was tested, what failed, what changed, and what was retested. Hazard identification must cover design, construction, operation, maintenance, shutdown, decommissioning, and abandonment. The objective is not to create a large hazard register. The objective is to discover how people, plant, environment, and production can be harmed, and then force the design to respond. Risk assessment evaluates consequence and likelihood. It identifies which risks can be eliminated, which can be reduced through passive or mechanical protection, which require operating controls, and which require an independent instrumented safety function. This sequence matters. Do not jump immediately to sophisticated automation. Remove hazardous inventory, reduce pressure, improve containment, separate hazards, provide mechanical relief, improve layout. Only after simpler protection measures have been applied should an instrumented protection layer manage the remaining intolerable risk. For every required safety function, define the initiating condition, trip point, required risk reduction, response time, final safe state, reset philosophy, alarm behavior, bypass controls, maintenance overrides, architectural limits, unwanted trip requirements, and operator interface. These requirements form the safety requirement specification. Without this specification, detailed design has no stable safety target. Verification asks whether each engineering phase was completed correctly. Validation asks whether the installed system actually performs the required function. Both are essential. A correct calculation cannot rescue a wrongly installed valve. A successful software test cannot prove that an impulse line is clear. A perfect drawing cannot compensate for an untested final element. The most dangerous instrumentation failures are often ordinary engineering failures hidden inside ordinary details. A transmitter may use the wrong material. A seal may be incompatible with the process. An impulse line may plug. A thermowell may fail under vibration. A sample system may release hazardous material. A detector may be installed where it cannot see the release. A shutdown valve may be used for normal control and become unavailable when protection is demanded. Every instrument and actuated valve must therefore be assessed for loss of electrical power, loss of instrument air, loss of hydraulic pressure, internal failure, communications failure, and restoration of energy. The design must answer one direct question. When this device fails, what does the process do next? Do not accept fail-safe as a label without analysis. Closing a valve may be safe for one scenario and dangerous for another. Holding the last position may preserve stability or trap hazardous energy. Opening a valve may depressurize equipment or feed a fire. The correct failure action comes from process analysis, not habit. Safety functions must remain independent from basic process control functions. Integration may improve visibility, but it must not create common failure paths. Safety sensors should use separate process connections. Safety wiring, junction boxes, input channels, output channels, logic, and final elements should be segregated wherever independence is claimed. Configuration access must be controlled so that a routine control change cannot silently weaken a protective function. A failed safety sensor is not a minor maintenance notification. It represents the loss of part of a protective layer. It must generate a clear alarm at a continuously attended location. Bypasses and maintenance overrides must be visible, controlled, time-limited, and alarmed. Emergency shutdown switches must be protected against accidental operation, clearly identified and easy to operate under stress. Use continuous transmitters instead of simple switches wherever practical. A continuous signal reveals drift, disagreement, and developing failure. A hidden switch may remain failed until the exact moment it is demanded. Early warning alarms should occur before the shutdown point so the operator has a realistic opportunity to recover the process without defeating protection. Final elements deserve equal attention. Shutdown valves must be dedicated to protection, correctly selected, properly sized, and testable. Redundant solenoid arrangements must be powered and monitored independently. Individual testing must be possible. Partial movement testing may support online assurance, but complete testing is still required at defined intervals. Fire and gas detection provides another independent layer. It acts after loss of containment and must detect the event early enough to isolate, shut down, depressurize, ventilate, alarm, or initiate other protective actions. Detector type, location, coverage, obstruction, environmental conditions, false alarm sources, maintenance access, and voting logic all matter. A detector installed in the wrong place is not protection. It is confidence without performance. The operator interface is also part of the safety design. Poor graphics, alarm floods, unclear priorities, inconsistent navigation, and badly located controls increase error precisely when the operator is under pressure. Displays must make abnormal conditions obvious, suppress redundant alarms, distinguish normal control from shutdown action, and place critical information where it can be understood quickly. Control rooms must support visibility, communication, access, maintenance, and future growth. Safety actions should be physically and visually distinct from routine controls. Equipment rooms need realistic space for panels, cable entry, heat dissipation, expansion, and safe working access. Space that appears generous during early design usually shrinks after supplier data, electrical equipment, structures, stairways, and cable routes are added. Packaged control panels require particular scrutiny. A supplier may offer a proven standard panel, but proven elsewhere does not mean compliant here. Local legislation, hazardous area requirements, ambient conditions, certification, required safety performance, alarm philosophy, communications behavior, and failure action must all be verified. Historical design is not a substitute for current compliance. Field equipment must be selected for the actual environment, not the catalog environment. Consider temperature, sunlight, chemicals, corrosion, marine exposure, fungi, rodents, vibration, flooding, dust, and mechanical damage. Materials must resist both the surrounding atmosphere and the process fluid. Hydrogen sulfide, carbon dioxide, chlorides, and contaminated surfaces demand coordinated material review across instrumentation, piping, process, and metallurgy. Lightning and electrical surge protection must prevent field disturbances from propagating into control and safeguarding systems. Critical instruments require suitable grounding, local surge protection, and coordinated protection at equipment rooms. Hazardous area design requires more than purchasing certified equipment. Certification must match the gas group, temperature class, protection method, area classification, installation method, cable entry, ambient rating, and local legal acceptance. The complete hazardous area record must remain controlled throughout the life of the facility. An expired, restricted, or incorrectly applied certificate can invalidate an otherwise capable instrument. Measurement design also carries containment risk. Pressure, flow, level, temperature, and process analysis systems need correct materials, pressure ratings, isolation, flushing, purging, sealing, drainage, and maintenance access. Thermowell strength and vibration calculations are essential because a failed thermowell can become both a projectile and a process release path. Process analysis systems must control sample pressure, temperature, transport delay, calibration gas, disposal route, return route, venting, and hazardous area impact. Cables are part of the safety function. They must survive the environmental, electrical, and fire conditions for which protection is claimed. Instrument and control cables must be separated from power cables to prevent interference and false signals. Intrinsically safe circuits must remain segregated from other circuits. Safety cables may require flame retardant construction, fire-resistant construction, physical protection, or passive fire protection so the plant can complete an orderly shutdown during a fire. Cable calculations must show their method, assumptions, voltage drop top, connected load, fault conditions, and stored energy limits where intrinsically safe circuits are used. Hidden calculation logic is not engineering assurance. Hydraulic systems introduce stored energy hazards. Reservoir size, response time, actuator torque, fluid consumption, cleanliness, pressure rating, pressure relief, coupling compatibility, and hydraulic fluid selection must be engineered as one system. A low-pressure fitting installed in a high-pressure circuit can create a lethal failure. Before maintenance, stored pressure must be positively released. Pneumatic systems depend on air quality, moisture control, filtration, pressure regulation, and correct material selection. Instrument air must never be assumed suitable for breathing. Installation can preserve the design or destroy it. Instruments must be accessible from permanent platforms or ground level, wherever routine inspection, calibration, or testing is expected. Designers should not create maintenance activities that require temporary scaffolding, awkward lifting, unsafe body position, or unnecessary exposure to operating equipment. Field equipment must not obstruct walkways, handrails, escape routes, valves, or access to other equipment. Labels must remain readable during daylight, darkness, rain, and normal operating conditions. Tubing and compression fittings must be compatible and preferably standardized to one manufacturer at each joint. Mixing ferrules, nuts, and fitting bodies from different manufacturers creates uncertainty in sealing and pressure containment. This requirement must extend to package suppliers, subcontractors, and field installation teams. Subsea control introduces a different risk profile. Human exposure may be lower, but environmental and financial consequences can be enormous. Hydraulic and electro-hydraulic systems require correct sizing, material compatibility, pressure containment, response analysis, voltage analysis, communications integrity, redundancy, spare hydraulic paths, and interfaces that diverse or remotely operated vehicles can connect and disconnect reliably. Umbilicals, flying leads, subsea control units, accumulators, valves, electrical conductors, hydraulic tubes, and connectors must be designed as one dynamic system, not as isolated purchased items. The final lesson is simple. Safety in instrumentation and control is not the responsibility of one review, one specialist, one calculation, or one shutdown system. It is the accumulated result of thousands of design decisions. You create safe design when requirements are explicit, independence is real, failure actions are understood, hazardous energy is controlled, alarms are usable, equipment is accessible, testing is complete, documentation is traceable, and every protective function can be proven from sensor to final element. Do not ask only, does the system work? Ask the harder questions. How does it fail? What happens when power returns? What if the sensor drifts? What if the operator is overloaded? What if a bypass remains active? What if the valve does not move? What if the cable burns? What if the supplier's standard package does not match the site? What if maintenance cannot safely reach the device? That is where real safety engineering begins. When you answer these questions early, you reduce redesign, avoid late project conflict, improve commissioning, strengthen operability, simplify maintenance, and protect people, plant, environment, and production. That is not additional engineering. That is competent engineering.